Hello, welcome to today's class. Today's class is again on logical agent, and this is the fifth class on this topic. In today's class, we will talk about logical equivalence, a deduction theorem, proof by refutation, and inference rules. First, we'll talk about logical equivalence. Two sentences alpha and beta are logically equivalent if they are true in the same set of models. So whichever models in which alpha is true, beta also has to be true. And similarly, in whatever models beta is true, alpha has to be true. So alpha and beta will be true in exactly the same set of models. This is the symbol for logical equivalence. This symbol means that alpha is logically equivalent to beta. As an example of logical equivalence, consider these two sentences. The first sentence is P and Q, and the second sentence is Q and P. Now, whichever model P and Q is true, in that model Q and P will also be true. And similarly, in whatever models Q and P is true, in that model P and Q will also be true. This you already know, and hence we can say that these two sentences are logically equivalent because they will be true in the same set of models. Now, any two sentences alpha and beta are equivalent only if each of them entails the other. So this is something new. It says that alpha will be logically equivalent to beta if and only if alpha entails beta and beta entails alpha. Why is it so? If you remember the definition of entailment, it says that alpha entails beta means beta will be true in all the models where alpha is true. But there may be some models where beta is true and alpha is false. Only requirement is if alpha is true, beta has to be true. But now when we put the condition that alpha entails beta and beta also entails alpha, then alpha and beta will be true in the same set of models. So from the first entailment, alpha entails beta, we know that if alpha is true, beta has to be true, but there may be other models where alpha is false and beta is true. So with only a single entailment, we cannot say that they are logical equivalent because there may be some models where beta is true but alpha is false. But as soon as we give the other entailment also, that beta entails alpha, now because of the second entailment, this cannot happen, that beta is true and alpha is false. Because beta entails alpha means whenever beta is true, alpha has to be true. Thus, when we have alpha entails beta and beta entails alpha, then the two sentences alpha and beta will be true in exactly the same models, which in other words means alpha will be logically equivalent to beta. Now let us talk about valid sentence. So what do we mean by valid sentence? A sentence is valid if it is true in all the models. An example of it is P or not of P. This particular sentence, in this sentence we have only one logical symbol, which is P, and hence we can have only two models, P equal to true and P equal to false. these are the only two models. And if you try to find out the truth value of this sentence, when P is true, this sentence will be true, and when P is false, then also this sentence will be true. So this particular sentence will be true in both the models possible, and hence P or not of P is valid because it is true in all the models. Valid sentences are also called tautologies. Now, if you remember, we introduced this propositional symbol true in one of the earlier class, and there we mentioned that the proposition symbol true will be true in all the models. And now we also say that a valid sentence will be true in all the models. Hence, in all the model that the valid sentence is true, our propositional symbol true is also true. And hence we can say that every valid sentence is logically equivalent to the proposition symbol true. Now let us talk about the deduction theorem. The deduction theorem says that for any sentences alpha and beta, alpha will entail beta if and only if the sentence alpha implies beta is valid, which means alpha implies beta has to be true in all the models. If alpha implies beta is true in all the models, it means that alpha will entail beta. Now, why is it so? We know that alpha implies beta means if alpha is true, then beta must also be true. That's the condition of entailment. If alpha is true, beta has to be true. But if alpha is false, then beta may be true or false. And we also know from one of our earlier class that alpha implies beta means this particular sentence alpha implies beta will be false. The only way that this sentence can be false is when alpha is true and beta is false. So if you look at the truth table that we studied in one of the earlier class, in the truth table you will see that alpha implies beta can be false only when alpha is true and beta is false. Otherwise, alpha implies beta will always be true. But if alpha entails beta, we know that alpha equal to true and beta equal to false cannot happen. If alpha implies beta, then alpha equal to true and beta equal to false cannot happen, because that's the definition of alpha entails beta. Now, since this condition cannot happen, that alpha is true and beta is false, this alpha implies beta will be true in all the models, because the only way that alpha implies beta will be false is when alpha is true and beta is false, and this cannot happen. Alpha equal to true and beta equal to false cannot happen because alpha entails beta. And if this only condition that can make alpha implies beta false cannot happen, it means alpha implies beta will always be true in all the models, and hence alpha implies beta is a valid sentence. And that's why we get this deduction theorem. However, it is if and only if, so it should apply in both the direction. So if alpha entails beta, then alpha implies beta will be valid, And if alpha implies beta is valid, then it means that alpha will entail beta. So from all this discussion, we can say that we can decide if alpha entails beta by checking whether alpha implies beta is true or not in every model. Now let us talk about satisfiable sentences. A sentence is satisfiable if it is true in some model. So it doesn't have to be true in all the model, but at least in some model it has to be true. If it is not true in any of the model, then it cannot be called satisfiable. Now satisfiability can be checked by enumerating all the possible models until one is found that satisfies the sentence. If we can find at least one, then we know the sentence is satisfiable. Now alpha is valid if and only if not of alpha is unsatisfiable. So this is a statement we are making, and this would be true because alpha is valid means in all the models alpha is true. Hence, not of alpha will be false in all the models. If alpha is true in all the models, not of alpha will be false in all the models. And now if not of alpha is false in all the models, it means not of alpha is not satisfiable. We don't have at least one model in which not of alpha is true. Now by contrapositive rule, we can also say that alpha is satisfiable if and only if not of alpha is not valid. We are making the same statement in a different way. We are saying that alpha is satisfiable if and only if not of alpha is not valid. That's true because if not of alpha is valid, it would mean that not of alpha is true in all the models. If not of alpha is true in all the models, it means that alpha is false in all the models. Now if alpha is false in all the model, alpha cannot be satisfiable. Hence, it cannot happen that not of alpha is valid. So if alpha is satisfiable, then not of alpha is not valid, and it will apply in both the direction. Now from the previous slide, we know that alpha entails beta if and only if the sentence alpha implies beta is valid. This was the deduction theorem. And from the previous two statements that we have made, now we can write this deduction theorem as shown here. Actually not based on the previous statements, it's based on the definition of alpha implies beta. Alpha implies beta is logically equivalent to not of alpha or beta. We will see that logical equivalence in the next one or two slides, where we will see that alpha implies beta is logically equivalent to not of alpha or beta. So this sentence alpha implies beta if and only if the sentence alpha implies beta is valid can be written as alpha implies beta if and only if the sentence not of alpha or beta is valid. And now we apply the previous statement that we made, that alpha is valid if and only if not of alpha is unsatisfiable. So here the statement is not of alpha or beta is valid. So this condition we can write as not of alpha or beta is unsatisfiable. Thus we can say that alpha entails beta if and only if the sentence not alpha or beta is unsatisfiable. And now if we apply De Morgan's theorem on this sentence, we will get alpha entails beta if and only if the sentence, when we apply De Morgan's theorem, we'll get alpha and not of beta is unsatisfiable. So all we need to do now is, if we want to find out whether alpha entails beta or not, what we need to do is we should add the not of beta and try to show that alpha and not of beta is unsatisfiable, which means you will not find at least one model in which alpha and not of beta is true. In all the models this will be false. Now proving beta from alpha by checking the unsatisfiability of alpha and not of beta is called the proof by refutation or proof by contradiction. Now we will talk about some inference rules. And the first inference rule that we will talk about is the modus ponens. So this rule modus ponens says that if alpha implies beta and alpha is given, then from these two sentences we can infer beta. As an example for this, let us consider this is our alpha. Alpha is Wumpus ahead and Wumpus alive implies should. So this is alpha and this is beta, and it's also given that Wumpus is ahead and Wumpus is alive. So now from these two sentences we can infer beta was should. So we can infer that should can be inferred. So the first one says that if Wumpus is ahead and Wumpus is alive, then we should. And the second sentence says that Wumpus is ahead and Wumpus is alive. So we can infer that we need to should. And that this inference rule that we used is called the modus ponens rule. Then there is another rule called And-Elimination, which says that if it is given that alpha and beta is given, then from this we can infer alpha, and actually we can also infer beta. Both are valid. So given alpha and beta we can infer alpha, given alpha and beta we can infer beta also. So when we have a conjunction, both the conjunct can be inferred. An example of it, so our alpha is Wumpus ahead, our beta is Wumpus alive. So if this is given, alpha and beta, Wumpus ahead and Wumpus alive is given, then we can infer that Wumpus alive can be inferred. Now here are some logical equivalents which you may already be knowing some of them. So the first two is the commutative law, which says that alpha and beta is logically equivalent to beta and alpha or beta is logically equivalent to beta or alpha. Similarly, the associativity of and the associativity of alpha also gives us two logical equivalents. Double negation also, you know, not of alpha is alpha. This may be something new, and this is what we used in one of the earlier slide, the contraposition, which says that if alpha implies beta, then we can say that not of beta implies not of alpha. So both of them are equivalent. Then implication elimination rules says that if alpha implies beta is logically equivalent to not of alpha or beta. We also applied this rule in one of the earlier slides. Then we have the biconditional elimination, which says that alpha biconditional beta is logically equivalent to alpha implies beta and beta implies alpha. Then we have the De Morgan's rule that you already know, and then we have the distributive rule in which you already know. Now from each of these logical equivalents, we can come up with some inference rule. For example, from the biconditional elimination, we can come up with the following inference rule. So if the left hand side is given, we can infer the right hand side. That's what is shown here. If alpha biconditional beta is given, then we can infer alpha implies beta and beta implies alpha. Also, if the right hand side is given, we can infer the left hand side. So if alpha implies beta and beta implies alpha is given, then we can make the inference that alpha biconditional beta. Now let us apply this inference rule to make some inference in the Wumpus game. This was the knowledge base we created in the previous class, and we gave names to each of the sentences. So we have 5 sentences, R1, R2, R3, R4 and R5 in our knowledge base. Now if we apply the biconditional elimination to rule R2, then we can derive a new sentence which is B11 implies P12 or P21 and P12 or P21 implies B11. And we name this new sentence R6. So by application of the biconditional elimination rule on R3, we come up with this sentence, new sentence called R6. Now we can apply And-Elimination on R6. Since this is a conjunction, the And-Elimination rule says that from a conjunction we can infer each of the conjunct. So given R6, I can infer B11 implies P12 or P21, and we can also infer P12 or P21 implies B11. And here we are inferring this part. P12 or P21 implies B11, and we call that the sentence, new sentence, R7. Now we will apply the contrapositive rule to R7, and the contrapositive rule says that if alpha implies beta, then not of beta implies not of alpha. So that contrapositive rule applied to R7 will give us not of B11 implies not of P12 or P21. And now we can apply De Morgan's we can apply modus Ponen. We will apply a modus Ponen between R8 and R4. So if we consider this alpha, if we consider this beta, alpha is not of B11, which we also have here. So alpha implies beta, comma, alpha is given. So we can infer beta, which is not of P12 or P21. So by applying modus Ponen, we can infer not of P12 or P21. And now if we apply De Morgan's theorem on R9, we get not of P12 and not of P21. Thus we see that by using this inference rule, we started with our initial knowledge base, and then we applied some inference rule, creating new sentences, and finally we make the inference that there is no pit. The meaning of this sentence is there is no pit in square 1 2, and there is no pit in square 2 1. So this is the inference we have now made by application of inference rules, and this was something we inferred through logical reasoning as a human also, but now we are doing the same logical reasoning through the application of inference rules. And we are not using model checking here to make the inference rule. In the previous class we again made the same inference by application, by enumerating all the models and checking whether the entailment is true or not. So in model checking we enumerated all the models. But now this is a new method where we are applying inference rules. However, these rules that we have applied, that first we will apply biconditional elimination, then we will apply And-Elimination, then we will apply contraposition. So in what order we will apply the rules was actually decided by us as a human. But we want a computer to be able to decide what inference rule to apply. And now this sequence of rules that needs to be applied can be found out using a search algorithm. Any search algorithm that we have studied so far can be applied to find out the exact sequence of rules that we should apply. But now when we want to use a search algorithm, we need to define the problem, where we need to specify the initial state, the list of actions that are possible in each state, and the result of each action, and the final goal state. and that is what is shown here. We can, as an initial state, the initial knowledge base will become our initial state. And how will we know what are the set of actions that are allowed in each state? This set of action consists of all the inference rules applied to all the sentences that match the top half of the inference rule. So if we have an inference rule whose top half is present whose top half is present in one of the sentence. For example, if I go back to explain it, so here we are applying the And-Elimination rule to R6, and the And-Elimination rule consists of this rule. So if we can find a sentence which match this top half of the rule, then we can apply that particular rule. So if we have a sentence which matches this top half, then we can apply that particular rule. So here we have a sentence which is a conjunction of these two conjunct. So this particular sentence matches the top half of the And-Elimination rule, and hence we can apply the And-Elimination rule. So which rules we can apply can be found out through the application of this sentence. And then the result will be the result of an action is to add the sentence in the bottom half of the inference rule to the knowledge base. So what would be the result of the action that we perform? The result was that whatever is in the bottom half of the inference rule, that will be added to the knowledge base as a new sentence. And the goal state is we should be able to reach the sentence that we are trying to prove. So when we want to solve the inference problem as a search problem, then we have to specify the inference problem in this way. We have to specify the initial state, we have to specify the actions, we have to specify the result, we have to specify the goal, and then we can use a search algorithm to find out the sequence of inference rule that we should apply. And now this method of making an inference is different from the earlier method of model checking, where we enumerated all the models. And at the last, I want to talk about monotonicity, which says that the set of entailed sentences can only increase as information is added to the knowledge base. To say it in a different way, for any sentences alpha and beta, if the knowledge base entails alpha, then after adding beta to the knowledge base, we will still be able to infer, we will still be able to entail alpha. So adding beta will not affect what we were able to entail earlier. So monotonicity means that inference rule can be applied whenever suitable premises are found in the knowledge base. The conclusion of the rule must follow regardless of what else is in the knowledge base. There may be something else in the knowledge base which is beta, but that should not affect what we can entail. So if KB can entail alpha, KB and beta will also be able to entail alpha. So with that, I would like to end today's class. We'll meet again in the next class. Thank you. Bye.